Right now, without any effort on your part, your body is drifting into a future that has not quite happened yet, at a pace so steady you have never once felt it change. Your heart is beating somewhere around once every second. Your lungs are filling and emptying in their slow tidal rhythm. And every one of those beats, every one of those breaths, is quietly carrying you forward, second by second, into a version of the world that did not exist a moment ago. You are, in the most literal sense, already moving through time. You always have been. You could not stop it if you tried. That might sound like an odd thing to point out, since it seems almost too obvious to mention. Of course you move through time. Everyone does. The clock on your nightstand does it. The moon does it. The dust settling on the windowsill does it. But the strange truth, the one that took physicists a very long time to fully appreciate, is that this motion through time is not fixed the way it feels. It is not the same steady drumbeat for everyone, everywhere, no matter what they are doing. It can bend, it can stretch. It can slow down or speed up, depending on how fast you are moving through space, and depending on how deep you are sitting in the gravitational pull of something massive. This is not science fiction. It has been measured, tested, confirmed, again and again, with instruments precise enough to catch differences smaller than a heartbeat's worth of drift, spread out over years. Let's start gently, with something you can almost picture as you lie there. Imagine a clock, not a digital one, but an old mechanical clock, the kind with a pendulum swinging back and forth in a wooden case, the kind that might have ticked quietly in a hallway 100 years ago while a family slept upstairs. Each swing of that pendulum marks off a slice of time, one tick, then a pause, then another tick. Now imagine two identical clocks like this, built by the same careful hands, calibrated to tick in perfect unison. Set them side by side, and they will agree with each other forever, or at least for as long as their gears hold together. But now, do something strange. Take one of those clocks and put it on a train. Let the train pull out of the station and pick up speed, rolling smoothly along the tracks into the night. According to a discovery made in the early years of the 20th century by a young patent clerk in Switzerland who spent his lunch breaks turning thought experiments over in his mind, that moving clock will now tick very, very slightly slower than the one that stayed behind on the platform. Not because anything is wrong with its gears, not because the motion is shaking it or disturbing it in some ordinary mechanical way. The slowing happens to time itself, for anything and anyone traveling with that clock. The passengers on the train are aging, thinking, breathing, all at a pace that is fractionally slower than the pace of the people they left behind on the platform, at least according to those people on the platform. This idea has a name, time dilation, though you don't need to hold on to the name so much as the feeling of it. The faster something moves through space, the slower it moves through time, relative to something that is staying still or moving more slowly. And here is the detail that makes it feel almost dreamlike rather than mechanical. Neither the person on the train nor the person on the platform notices anything unusual happening to them personally. Their own heartbeat feels perfectly normal. Their own thoughts unfold at their own normal pace. It is only when you compare the two afterward, when the train pulls back into the station and the two clocks are set beside each other again, that a tiny, measurable gap appears. The traveling clock is behind, not broken, behind. For an ordinary train, this effect is almost impossibly small, smaller than anything you could ever notice in an entire lifetime of train rides. You would need speeds far greater than any train, any car, any airplane, to make the gap large enough to matter to a human life. But scientists have tested this with things that do move at tremendous speeds, things like subatomic particles racing through particle accelerators, and with ordinary atomic clocks flown around the Earth on commercial airliners. In one especially memorable experiment, back in 1971, two physicists named Joseph Hafele and Richard Keating loaded extremely precise atomic clocks onto commercial flights, flew them around the world in both directions, and then compared them to identical clocks that had stayed on the ground at the United States Naval Observatory. The traveling clocks came back having ticked a different amount than the stationary ones, by a matter of billionths of a second, but exactly in the direction and the amount that the equations predicted. The difference was small, but it was real, and it was there in the data, printed out on paper, undeniable. So this is where we can say something quietly astonishing, something worth letting settle in the dark, like a stone, sinking slowly through still water. Ordinary time travel, travel into the future, is not a fantasy, it is not a metaphor. It is a measured, repeatable, thoroughly confirmed feature of how the universe works. Every time you fly on an airplane, you age a tiny, tiny bit less than someone who stayed on the ground, because you were moving relative to them. Every astronaut who has spent months aboard the International Space Station, orbiting the Earth at roughly 17,000 miles an hour, has returned to Earth having aged a few milliseconds less than the people who stayed behind. The Russian cosmonaut Gennady Padalka, who has spent more cumulative time in orbit than any other human being, has effectively traveled about 1/40th of a second into his own future, compared to someone who never left the ground. It is a small step, but it is a real one, taken by a real person, verified by real clocks. There is a second version of this effect too, one that has nothing to do with speed and everything to do with gravity. The same discoverer, who worked out the puzzle of the moving train, later realized that gravity itself bends time, and that clocks sitting deeper in a gravitational field, closer to a massive object like the Earth, tick more slowly than clocks sitting farther away. This means, in a way that is almost too strange to say out loud, in a quiet room like this one, that your feet are aging very slightly slower than the top of your head, right now, because your feet are just a little bit closer to the center of the Earth's gravity, a little bit deeper in its gravitational well. The difference is unimaginably tiny, far too small for any device you own to detect, but it has been measured in laboratories using clocks placed at different heights, sometimes just a matter of centimeters apart, and the clocks disagree in exactly the way the equations say they should. Put these two effects together, motion and gravity, and you start to see why the question of time travel is not really a question of whether it is possible. It already is possible, in this gentle, forward-moving sense. The real question, the one that has occupied physicists for over a century now, the one we will spend the rest of this journey unfolding slowly and carefully, is something much bigger and much stranger. It is this: if time can stretch and bend, depending on speed and gravity, are there conditions extreme enough, environments strange enough, mathematics permissive enough, to let that bending become dramatic instead of tiny? Could a future traveler, given enough speed, or given proximity to something massive enough, leap forward, not by fractions of a second but by years, by decades, by centuries, arriving in a future utterly unrecognizable compared to the world they left? And is there any way, even a purely theoretical one,
for that bending to fold back on itself, to create a path not just forward, but somehow backward as well. These are not settled questions. Some of what we will explore together over the coming sections rests on solid, repeatedly tested physics, the same kind of physics that keeps your GPS satellite accurate and that let those airplane clocks disagree in exactly the predicted way. Other parts of what we will explore live much further out, in the realm of mathematical possibility, exotic matter, and equations that may or may not describe anything that could ever actually exist in our universe.
We will move through all of it slowly, gently, without rushing past the confusing parts, because the confusing parts are exactly where the good sleep thoughts live. For now, let this first idea rest quietly in your mind as you keep breathing, keep drifting, keep moving forward into the next moment the way you always have. You are, and always have been, a time traveler of the simplest kind. And having settled that, softly and without fanfare, we can let ourselves wonder what it might mean to travel not just steadily forward, but to ride alongside light itself, and to ask what light experiences that we do not. Before we can ride alongside light, even in imagination, we need a few quiet tools, not equations, just ways of thinking. So let your mind loosen a little further, and let's build these tools slowly, one at a time, the way you might lay out smooth stones on a table before a long, careful game. The first tool is the idea of an event. In everyday speech, an event is a party, a wedding, something with balloons. But in physics, an event is something much smaller and much more precise. An event is a single point, a single instant, located at one particular place and one particular time. A match striking, a raindrop touching a windowsill, the moment a clock's second hand crosses 12. Each of these is an event, because each one happened at a specific here and a specific now, and nowhere else, and no other time. This sounds almost too simple to mention, but it turns out to be the foundation of everything that follows, because relativity is, in its bones, a theory about how different observers describe the same events differently, while agreeing, underneath all their disagreement, on certain deeper facts. Which brings us to the second tool, the observer. An observer, in this context, is not necessarily a person. It can be a person, certainly, sitting on a train platform with a pocket watch, but it can just as easily be a satellite, a beam of instruments, a clock bolted to a wall. What matters is that an observer has a position and a motion, a particular vantage point from which events are measured and timed. And crucially, different observers, moving differently, can measure the same event and come away with different numbers for when and where it happened. Not because anyone is confused, and not because any instrument is broken, but because the numbers themselves depend on who is doing the measuring and how that measurer is moving through space. This leads naturally to the third tool, which is the reference frame. Think of a reference frame as the entire coordinate system an observer carries with them, an invisible scaffolding of rulers and synchronized clocks that extends outward in every direction, moving along with them. If you are sitting in a parked car, your reference frame is at rest relative to the ground. If you are riding in a car moving at 60 miles an hour down a quiet highway, your reference frame moves with you, at 60 miles an hour relative to the ground, but at 0 relative to yourself. You feel still. Your coffee cup feels still, sitting undisturbed in its holder.
Everything inside your moving frame behaves, to you, exactly as if you were not moving at all. This is not a trick of perception. It is one of the oldest and most well-tested ideas in physics, going back long before Einstein, to Galileo, who noticed that a sailor below decks on a smoothly moving ship cannot, by dropping objects or watching insects fly, determine whether the ship is moving or standing still in harbor.
Uniform motion, motion without acceleration, without jolts or turns, is in a very real sense invisible from the inside. Now here is where things begin to gently bend. If motion is invisible from the inside, and if there is no experiment you can perform, sealed away in a windowless room, that tells you whether you are standing still or gliding smoothly through space. Then something has to give when we start asking questions about light. Because light behaves strangely, and this strangeness is the fourth tool we need, arguably the most important one of all. In the late 1800s, physicists were fairly confident that light, like sound, needed something to travel through. Sound moves through air, compressing and releasing it in waves, and it cannot cross the vacuum of space, which is why explosions in movies are, strictly speaking, silent events dressed up with sound design. Physicists assumed light must be similar, that it moved through some invisible, undetectable substance filling all of space, something they called the luminiferous ether. And if that were true, then the speed of light, measured from Earth, should differ slightly, depending on the direction you measured it, because the Earth itself moves through space, plowing through this hypothetical ether the way a swimmer moves through still water, faster relative to the current in one direction, slower in another. In 1887, two American physicists, Albert Michelson and Edward Morley, built an extraordinarily sensitive instrument in a basement in Cleveland, designed to detect exactly this difference. They split a beam of light, sent the two halves along perpendicular paths, bounced them off mirrors, and brought them back together to look for the tiny mismatch that ether drift should produce. They found nothing, no mismatch, no matter which direction they pointed the device, no matter what time of day or season they tried. Light seemed to move at exactly the same speed, regardless of Earth's motion through space. This was a deeply unsettling result, the kind of experiment that quietly undermines an entire framework of assumptions, and it sat there, puzzling and unresolved, for almost 2 decades. Then, in 1905, working not in a grand laboratory, but in a patent office in Bern, Switzerland, evaluating other people's inventions during the day, and turning over questions of light and motion in his own mind during evenings and lunch breaks, a young physicist named Albert Einstein proposed something audacious. What if the null result of Michelson and Morley wasn't a puzzle to be explained away, but a clue to be taken completely at face value? What if the speed of light in a vacuum truly is the same for every observer, no matter how they are moving, no exceptions, no ether, no cosmic current to swim against? Not because light is somehow magical, but because this constancy is simply a basic feature of how space and time are stitched together. This single assumption, taken seriously and followed through with unflinching logical care, forces something remarkable. If two observers are moving relative to each other, and both of them measure the speed of a passing beam of light, and both get exactly the same number, then something else, something we normally treat as fixed and universal, has to be flexible instead. That something is simultaneity, our sense of what counts as happening at the same time. Here is a gentle way to picture it.
Imagine a long train moving smoothly down a straight track, and imagine a flash of light released from the exact center of one of its train cars, spreading outward toward both ends at once. To a passenger sitting inside that train car, the light reaches the front wall and the back wall at exactly the same moment, because the distances are equal and the speed is equal in both directions. Simple enough. But now imagine someone standing outside on the embankment, watching the train glide past. From their vantage point, the train is moving forward, which means the back wall of the car is rushing slightly toward where the flash occurred, while the front wall is rushing slightly away from it. The light still travels at that same fixed, unchanging speed in every direction, because that is the one rule that cannot bend. But because the walls themselves are moving, the light reaches the back wall microscopically, sooner than it reaches the front wall, from the outside observer's point of view. Notice what just happened. Two events. The light touching the back wall, and the light touching the front wall, are simultaneous for the passenger inside the train, and not simultaneous for the person watching from the platform. Neither observer is wrong. Neither clock is broken. Neither person made an error in measurement. They simply occupy different reference frames, moving relative to one another, and simultaneity itself. This thing we quietly assume is absolute and shared by everyone everywhere, turns out to be something that depends on your motion. This naturally brings us to a distinction worth holding gently in mind as you drift, because we will return to it again and again throughout this journey. There is a difference between the time that elapses for a particular observer, measured on a clock that travels along with them through their own personal, unbroken thread of experience, and the time that a different, outside observer would assign to that same stretch of experience. Physicists have a name for the first kind. They call it proper time. The time ticked off by a clock that stays with you, in your pocket, on your wrist, quietly marking the seconds of your own particular journey through the universe. Proper time is, in a sense, the most personal measurement there is. It belongs to you, and only you, to your specific path through space, and through moments. And this is the deep, quiet point underlying everything relativity tells us about clocks disagreeing. It is never that a clock breaks, or slows down mechanically, or malfunctions under speed or gravity, the way a watch might stutter if you dropped it. Every clock, everywhere, ticks its own proper time perfectly, faithfully, without complaint. What changes, what genuinely differs between observers, is how much elapsed time accumulates along different paths through space-time, paths that can stretch or compress relative to one another, depending on how fast you travel, and how deep into a gravitational well you sit. Your clock is not lying to you. It is simply telling the truth about your particular journey, which may not be the same truth another traveler's clock is telling about theirs.
Let's follow that idea somewhere very small and very fast, because that is where physicists first found the proof that this strange bending of time was not just a thought experiment, but a measurable fact about the world. Picture a muon. It is a small subatomic particle, a heavier, more restless cousin of the electron, and it does not last long. Left alone in a laboratory, at rest, a muon survives on average about 2/millionths of a second before it decays into other particles. 2/millionths of a second is such a brief flicker that it barely deserves the word duration. And yet, high above your head right now, muons are being created constantly in the upper atmosphere, about 15 kilometers up, when cosmic rays from deep space slam into air molecules with tremendous energy. These collisions spray out showers of muons, and those muons go rushing toward the ground at speeds very close to the speed of light. Here is the puzzle physicists noticed decades ago. If you do the simple arithmetic, using that 2/millionths of a second lifetime, and even the very fastest speed a muon could travel, the particle should only cover a few hundred meters before decaying into something else. It should never make it down through 15 kilometers of atmosphere to reach a detector on a mountaintop or in a valley. And yet, detectors do register enormous numbers of these muons arriving at the surface, far more than that simple arithmetic would allow. For a while, this looked almost like a small crack in the tidy laws of the universe, a bookkeeping error that nature had apparently made without noticing. But there was no error. There was only the muon's own experience of time, its own proper time, differing from the experience of a physicist standing still on the ground with a stopwatch. From the muon's perspective, it lives its ordinary 2/millionths of a second life, no different, no stretched, no unusual. But because the muon is moving so close to the speed of light relative to the ground, the observer standing on the ground sees that brief muon lifetime dilated, stretched out, elongated, the way a shadow stretches long and thin when the sun sits low near the horizon. To the ground-based physicist, the muon appears to live many times longer than 2/millionths of a second, long enough, comfortably, to make the journey down through the atmosphere and land inside a waiting detector. The muon is not doing anything mysterious. It is simply following its own clock faithfully, while the observer on the ground is watching that clock from a different frame of motion, one in which the muon's brief life gets visibly, measurably lengthened. This is worth sitting with for a moment, because it is easy to imagine that time dilation is a delicate effect, something so tiny it could only ever matter in some hypothetical spaceship traveling at outrageous, unreachable speeds. But the muon shower above your head, arriving silently, invisibly, all through the day and night, all through your entire life, is direct, everyday evidence that moving clocks really do run differently than clocks at rest. Right here, in the ordinary sky, over your ordinary house. Atomic clocks tell the same quiet story, with even more precision. In 1971, two physicists, Joseph Haffel and Richard Keating, carried a set of cesium atomic clocks onto commercial airliners and flew them around the world, first eastward, then westward, while a matching set of clocks stayed behind on the ground at the United States Naval Observatory. Cesium atomic clocks are extraordinarily precise. They keep time by counting the natural, unwavering oscillations of cesium atoms, oscillations so regular that these clocks would drift by less than a second over millions of years. And still, after the flights landed, the traveling clocks disagreed with the stationary ones by tiny fractions of a second, amounts predicted almost exactly by the equations of relativity, once you accounted for both their speed relative to the ground and their altitude, since gravity too, as we will explore later, has its own quiet influence on the pace of time. The clocks that flew eastward, moving faster relative to Earth's rotation, came back showing slightly less elapsed time than the ground clocks. The clocks that flew westward, effectively moving slower relative to the spinning Earth beneath the aircraft, came back showing slightly more. This is not a hypothetical.
It is not a philosophical puzzle dressed up in scientific language. It is a measured, repeated, thoroughly confirmed feature of how time actually behaves. So well confirmed that it now sits underneath something you may have used earlier today, without a single thought about relativity at all. Your phone's GPS. The satellites that make GPS work orbit the Earth at roughly 14,000 kilometers per hour, and they sit far above the pull of Earth's gravity compared to a receiver on the ground. Both of these facts shift the ticking of the atomic clocks aboard each satellite. The satellite's motion, slowing its clock down slightly compared to clocks on the ground, and its distance from Earth's gravity, speeding its clock up slightly compared to clocks on the ground, since gravity, as we will see, also stretches and compresses time. These two effects do not cancel out. They partially offset one another, but a net difference remains, and if engineers had simply ignored it, if they had assumed all clocks everywhere tick at the same universal rate, the satellite clocks would drift out of sync with ground clocks by about 38 microseconds each day. That sounds impossibly small, a sliver of time no human sense could ever notice. But GPS calculates your position by timing how long radio signals take to travel from satellite to receiver, and light travels so fast that a timing error of even a few microseconds translates into a position error of several kilometers.
Without correcting for relativity, your GPS would slowly become useless, drifting further and further from your actual location, block by block, then neighborhood by neighborhood, within a single day. So the engineers who built the system quietly adjusted the satellite clocks before launch, tuning them to run at a very slightly different rate on the ground, so that once they reached orbit and experienced both their speed and their altitude, they would tick in step with clocks down here. Relativity is not an abstract curiosity confined to physics classrooms. It is baked, silently, invisibly, into the machinery that tells you which street you are on. All of this brings us, gently, to the most famous and most frequently misunderstood scenario in all of relativity, the twin paradox. Imagine two twins, born on the same day, starting their lives with perfectly synchronized clocks. One twin climbs aboard a spacecraft and travels away from Earth at a significant fraction of the speed of light, journeys outward for some years by her own experience, then turns around and travels back. The other twin stays home, living an ordinary life on Earth. When the traveling twin returns, she finds that her sibling has aged more than she has, not because time played a trick on either of them, and not because one twin's biology worked differently, but because they took two genuinely different paths through space-time, and those two paths simply do not accumulate the same amount of proper time. People sometimes call this a paradox, because if you only remember that motion is relative, you might think each twin should see the other as the one who is moving, and therefore each should expect the other to have aged less, which seems like a contradiction. But the situation is not actually symmetric between them, and this is where the distinction we set aside a moment ago becomes essential. The earthbound twin remains in a single, unaccelerated frame the entire time. The traveling twin does not. At some point, she must slow down, turn around, and come back, and turning around requires acceleration, a genuine, physically real change in her state of motion that the earthbound twin never experiences. That acceleration breaks the symmetry between them. It is the reason their two proper times end up genuinely, measurably different, rather than merely each side politely disagreeing about who moved. And yet, if you press further into the physics, acceleration itself
turns out not to be quite the deep explanation it first appears to be, more a signpost than the actual cause.
The truer explanation, the one that satisfied physicists once they worked through the mathematics carefully, has to do with the shapes of the two paths themselves through the four-dimensional fabric of spacetime, paths called world lines. The earth-bound twin traces a simple, straight world line moving steadily forward through time in one place. The traveling twin traces a bent, angled world line, journeying outward and then curving back to meet her sibling again. And it is a peculiar, almost dreamlike feature of spacetime's particular geometry, one that inverts the ordinary logic of distances you might carry from everyday geometry, that among all possible paths connecting two events in spacetime, it is the longest, most direct one, the straight world line, that accumulates the most proper time, not the least. Let your body settle a little further into wherever it's resting now. Nothing here requires effort. This next part is about a different kind of time difference, one that has nothing to do with speed at all. This one comes from gravity, and it starts, oddly enough, in an elevator. Imagine you're standing inside an elevator, and the cables have been cut. You're falling. Everything inside falls with you, at exactly the same rate, so relative to the elevator, nothing seems to be happening. Your feet don't press against the floor. A pen released from your hand doesn't drop, because it's falling exactly as fast as you are. For those few seconds before the ground arrives, you'd feel weightless, as though gravity had simply switched off. Now imagine the opposite scenario. You're in a windowless elevator sitting somewhere in deep space, far from any planet, and a rocket attached to it is firing steadily, accelerating you forward at a constant rate. You'd feel pressed against the floor, just as you would standing on Earth. If you dropped that same pen, it would fall to the floor, because the floor is accelerating up to meet it. And here's the strange part Einstein noticed. From inside the elevator, with no windows, there is no experiment you could perform that would tell you which situation you were in. Standing still on a planet, feeling its gravity, feels physically identical to being accelerated through empty space at the right steady rate. He called this the equivalence principle, and it became one of the load-bearing walls of general relativity. If acceleration and gravity are, in this deep sense, the same thing wearing different clothes, and we already know from the traveling twin that acceleration affects how much time accumulates along a path, then gravity should do something similar, and it does. Being deep in a gravitational field turns out to be physically comparable to constantly accelerating, which means clocks sitting at different depths in a gravitational field, so to speak, should tick at different rates, in a way that has nothing to do with anyone moving through space at all. Let's make this concrete, because the abstraction can get slippery late at night. Picture two clocks. One sits at the bottom of a very tall building, at street level. The other sits at the very top, high above the ground, on the roof. Both clocks are perfectly identical, manufactured on the same day in the same factory, calibrated against each other before being placed. And yet, once they're in position, the clock on the roof will run very slightly faster than the clock on the ground, not because anything is wrong with either clock, not because the air is different or the temperature or anything so mundane. It's because the clock at street level sits deeper within Earth's gravitational field, closer to the planet's mass, and the clock on the roof sits a little further out. This isn't a thought experiment dreamed up for a physics lecture and left untested. It's been measured directly and with remarkable precision. In 2010, physicists at the National Institute of Standards and Technology built an atomic clock so precise that they could detect a difference in the flow of time caused by raising it just 1 foot, about 30 centimeters, off the ground. 1 foot. The clock at the higher position ticked faster than the one below it, by an amount so small it would take many years to accumulate a single noticeable second, but the difference was there, measured, real, exactly matching what the equations predicted. If you've ever stood at the base of a staircase and then climbed to the top, you have, in the most literal and unromantic sense, aged very slightly, more at the top than you would have if you'd stayed at the bottom, for as long as you remained there. The difference is unimaginably tiny, far too small to notice in any human lifetime, but it is not zero, and it is not hypothetical. This effect is called gravitational time dilation, and once you start looking for it, it shows up in places that matter a great deal, not just in laboratory curiosities. Consider satellites. The global positioning system, the network of satellites that lets a phone in someone's pocket know exactly where it is on Earth, depends on extraordinarily precise timekeeping. Each satellite carries an atomic clock, and those clocks orbit roughly 20,000 kilometers above the surface, far higher up than the tallest building, far higher than any mountain. Because they sit that much further from Earth's mass, sitting in a weaker gravitational field than clocks on the ground, their clocks run faster than identical clocks down here, by about 45 microseconds each day, from gravity's influence alone. There's also a competing effect from the satellite's orbital speed, the same kind of time dilation we talked about with the traveling twin, which runs in the opposite direction and slows their clocks down by about 7 microseconds a day. Add both effects together, gravity speeding them up, motion slowing them down, and the satellite's clocks end up running about 38 microseconds faster than clocks on the ground, every single day. 38 microseconds sounds like nothing, a sliver of time too small to register in any human sense. But GPS depends on comparing the exact timing of signals traveling at the speed of light, and at that speed, a timing error of a few microseconds translates into a position error of several kilometers. If engineers hadn't corrected for this, built the adjustment directly into the satellites before launch, the system would drift further and further off, and within a single day, GPS would become essentially useless, guiding you to the wrong street, the wrong town. Every time a phone or a car finds its way somewhere using satellite navigation, it's quietly relying on Einstein's equations being correct, down to fractions of a millionth of a second. It's a strange thing to consider, that somewhere in the design documents for the GPS system are lines that exist purely because time itself does not flow at the same rate everywhere. If a foot of elevation and 20,000 kilometers of orbit can make measurable differences, it's natural to wonder what happens in places where gravity gets far more intense than anything on or above Earth. This is where neutron stars enter the picture. A neutron star is what remains after a massive star has exhausted its fuel and collapsed in on itself, crushing an amount of matter greater than our sun's down into a sphere often no wider than a city, something like 20 kilometers across. The gravity at the surface of a neutron star is almost impossible to describe in terms that feel real. A clock, sitting on such a surface, if it could somehow survive the conditions, would run noticeably slower, not by microseconds, but by a fraction that a distant observer could actually perceive over the course of ordinary observation. Minutes ticking by like tens of seconds, depending on exactly how compact the star is. And then, there are black holes, where this effect is pushed to
to its most extreme expression. A black hole forms when an object collapses so completely that its gravity becomes strong enough to prevent even light from escaping, past a boundary called the event horizon. As you get closer and closer to that boundary, imagine lowering a clock toward it on some impossibly strong cable. The clock would appear, to someone watching from a safe distance, to run slower and slower. Not because the clock itself has changed or broken, but because you're watching it from a region where time is passing at a different rate than where the clock now sits. As the clock approaches the event horizon itself, an outside observer would see it appear to slow almost to a stop, its hands seeming to freeze, its light stretching and dimming, taking longer and longer to climb back out to reach your eyes. The clock, from its own vantage point, would notice nothing strange at all. It would simply keep ticking normally, 1 second at a time, all the way down. That gap, between what the falling clock experiences and what the distant observer sees happening to it, is one of the strangest and most carefully studied ideas in all of physics, and it's where we're headed next, into what falling toward a black hole would actually mean for the person doing the falling, and for everyone watching from far away.
Let's set the black hole aside for a moment, gently, and come back to something more within reach. Because if we actually wanted to travel forward in time, not as thought experiment but as engineering problem, we wouldn't start with a black hole. We'd start with something more modest, more survivable. We'd start with speed. You already know the ingredients. Moving fast slows your clock relative to everyone who stayed still. Sitting in strong gravity does the same thing. Combine them, and you have two separate levers for reaching into the future, both grounded in effects that have been measured, both real, both available in principle to a species patient and resourceful enough to use them. Not to travel backward, never backward, but forward, in the sense of arriving at a later moment in the outside world, while your own body has aged less than the calendar would suggest. So, let's do the arithmetic slowly, the way you'd work out a recipe you've never tried before, checking each step before moving to the next. Imagine a ship capable of reaching 90% of the speed of light. That's already an almost unreasonable request, but let's grant it, for the sake of understanding the shape of the problem. At 90% of light speed, time dilation gives you a factor of a little more than 2. That means, for every year that passes for the crew, a bit over 2 years pass back on Earth. Take a 5-year voyage out and back, from the crew's perspective, and you'd return to find Earth roughly 11 years further along. Noticeable, strange, in a quiet way. Friends have aged more than you have, but not disorienting on a civilizational scale. Push the speed further, and the curve doesn't rise gently. It rises the way a hill turns into a cliff. At 99% of light speed, the factor climbs to about 7. At 99.9%, it's over 22. At 99.jojo%, past 40. The closer you creep toward the speed of light, the more violently the ratio bends, so that the last few decimal points of speed matter more than everything before them combined. A ship that spent 1 year, by its own clocks, cruising at 99.jojo% of light speed, might return to find more than 100 years had passed for everyone who stayed home. This is not exaggeration. It's the same equation that governs the muons falling through the atmosphere, scaled up to a human time scale. But here's where the calm, sleepy arithmetic runs straight into a wall made of energy, and it's worth sitting with that wall for a moment, because it explains why nobody is building this ship in a garage. To accelerate any object with mass
to speeds approaching that of light requires energy that grows without any friendly upper bound. Not linearly, the way pushing a shopping cart faster takes a bit more effort each time. It grows toward infinity as you approach the speed of light, which is really just another way of restating why nothing with mass can ever quite reach it. Physicists sometimes express this by saying the object's effective mass increases as it speeds up, resisting further acceleration more and more fiercely, though it's probably gentler to think of it simply as the universe charging an ever steeper toll for each additional fraction of a percent of speed. To get even a modestly sized spacecraft to 90% of light speed using anything resembling conventional propulsion would require more energy than humanity currently produces in a very long stretch of collective history. Chemical rockets, the kind that lifted Apollo astronauts off the launch pad, are almost comically unsuited to the task. Their exhaust leaves the nozzle at a few kilometers per second, a rounding error compared to what's needed. Even nuclear propulsion, which has been seriously studied since the 1950s in projects with names like Orion, imagining a ship pushed forward by a series of small nuclear detonations behind it, gets you to perhaps 1/10 of light speed at best, and even that comes with enormous unsolved engineering and safety problems. The only propulsion concepts that theoretically scale toward relativistic speeds tend to involve converting matter directly into energy with near total efficiency, something like a ship carrying both matter and antimatter, annihilating tiny controlled amounts of each to produce thrust. It's physically permitted. Nothing in the equations forbids it. But producing, storing, and safely using antimatter in the quantities required remains, for now, a problem more theoretical than practical, closer to alchemy than engineering, at least by the standards of what we can currently build. And even if you solved propulsion, you'd run headlong into a second problem, one that's almost poetic in how it punishes speed with the exact thing speed was supposed to buy you. At a meaningful fraction of light speed, the empty space in front of your ship stops being empty. Every stray hydrogen atom, every speck of interstellar dust, ordinarily harmless, drifting at a snail's pace relative to anything, suddenly slams into your hull at a significant fraction of the speed of light. From the ship's reference frame, that hydrogen atom carries kinetic energy comparable to a proton fired from a particle accelerator. Spread across billions of such collisions per second, the front of a fast-moving starship would need shielding capable of absorbing what amounts to a continuous, low-grade bombardment of radiation, uncomfortably similar to standing in front of a research reactor, except it never turns off for the length of the voyage. Engineers who study this problem seriously talk about shields made of ice, or magnetic fields strong enough to deflect charged particles before they reach the hull, ideas that remain, for now, comfortably theoretical. Let's set the danger aside for a moment, and think instead about something gentler, the practical business of getting up to speed at all, because even here, comfort imposes its own limit. A human body tolerates sustained acceleration reasonably well if it's kept modest, something close to the pull of Earth's gravity, 1g, felt as ordinary weight rather than crushing force. Accelerating continuously at 1g, a ship would take about a year, by its own clock, to approach a meaningful fraction of light speed.
That's actually a rather pleasant thought to end a description with, since it means a voyage of gentle, constant acceleration wouldn't feel violent at all. The crew would simply feel Earth-normal gravity the whole way, created not by spinning or by a planet's mass, but by the ship's own engines pushing steadily from behind. They could walk, sleep, eat meals that stayed on the table, for the entire outbound leg, and again for a symmetrical deceleration at the far end, and then the whole sequence reversed for the trip home. It's one of the more comforting pieces of relativistic travel. The discomfort isn't really about the sensation of speed. Nobody feels speed itself. What limits us is the energy needed to sustain that gentle push for long enough, and the radiation waiting in the space ahead. Now imagine you've solved all of it, somehow. The propulsion, the shielding, the sheer scale of energy. You've spent, from your own perspective, a few years threading a careful path outward and back, always accelerating gently, always feeling ordinary weight beneath your boots. What would it actually be like to come home? The earth you left would not simply be older. It would be, in some sense, a foreign country, separated from you, not by geography, but by time itself, in a way no ordinary traveler has ever quite experienced. Depending on how extreme your journey was, you might return to find decades had passed, technology transformed, languages drifted, familiar buildings gone or rebuilt, people you knew, grown elderly, or no longer living at all. There would be no going back to correct course, no way to check in partway through and adjust. Once you commit to speeds that stretch time this severely, the decision is close to permanent, a one-way door into a future you can visit, but never quite return from in the way you left it. There's something quietly humbling in that. Every clock aboard the ship would have told the truth the entire time, ticking along faithfully, one second after another, exactly as it should. And yet the story those seconds added up to would be a different story than the one written by the clocks left behind on Earth, both equally correct, both simply keeping honest time in the reference frame they happen to occupy. It isn't a malfunction, it isn't an illusion, it's just what happens when you ask two clocks to disagree about something as basic as how much time has passed, and then send one of them on a long, careful, extremely fast trip. Navigation, in this kind of future, would carry its own peculiar puzzles too. Questions about how you'd even find your way home to a planet that has, from your perspective, barely moved, while carrying instruments built to expect a much younger Earth waiting for your return. Let's set navigation aside for a moment and try something gentler. Let's draw a picture. Not a picture of stars or ships, but something simpler. A picture of time itself, sitting right next to space, on the same page. Physicists call it a space-time diagram, and if that phrase sounds intimidating, let it go. Think instead of something you may have made as a child without knowing it had a name, a chart with two lines crossing, one going up, one going sideways. Up is time, sideways is space, and every dot on that page, every single point, is a place and a moment fused together, a single here and now that will never come again in quite that combination. Picture yourself sitting still in a chair, reading, for 1 full hour. If someone were to plot that hour on our little chart, sideways position barely changing at all, you're not really going anywhere, but time keeps climbing, minute by minute, straight up the page. Your path traces a vertical line. 4. Now picture instead that you get up and walk briskly across the room, while that same hour ticks by. Your line tilts a little now, leaning to the side, as you cover distance, while time still marches upward. The faster you move through space, the more that line leans over, the closer it drifts toward horizontal. And there is, it turns out, a limit to how far it can lean. Light itself, in this picture, draws lines tilted at the steepest possible angle allowed. The fastest anything can cross the page. Nothing can lean over further than that. Now here's where the picture becomes something more than a picture. Imagine standing at a single point on this chart, this one moment, this one place, like a candle set down on a dark table. From that point, light spreads outward in every direction at once, the way ripples spread from a stone dropped in still water. Except here, the ripples aren't spreading through water, they're spreading through time itself, moving forward. If you drew all the paths that light could take from that candle, moving outward through every possible direction in space, while time also climbs upward, you'd get a shape. Not a flat ripple this time, but something like two cones joined at their tips, one opening upward into the future, one opening downward into the past, meeting exactly at that one point where the candle sits. This shape has a name, and it's a good one, because it really does look the way it sounds, the light cone. Everything inside the upper cone, every point that light could reach if it left this moment and traveled outward, represents a place and a time you could, in principle, ever influence. Not necessarily easily, not necessarily practically, but in principle. A signal, a nudge, a single photon sent out from here could reach any of those points, given enough time. That's your future light cone, the entire reachable future stretching out ahead of this one moment, like the beam of a lighthouse sweeping forward through the years. And the lower cone, opening downward into the past, is its mirror. It contains every point from which light could have reached you, right here, right now. Every event capable, in principle, of having influenced this exact moment you're living in. That's your past light cone. Somewhere within it sits the sun's light, leaving its surface 8 minutes before it warms your face. Somewhere further back within it sits far older light, from stars whose glow is only now, after an unthinkable stretch of years, arriving to be seen by a particular pair of eyes, on a particular quiet night. What lies outside both cones, off to the sides, is where things get strange, and where causality itself starts to show its rules. Think of the two cones together as sorting all of existence, from this one point's perspective, into 3 neighborhoods. There's the world you could affect, up in the future cone. There's the world that could have affected you, down in the past cone. And then there's everything else, the vast region lying outside the cones entirely, sideways from you on the diagram, which is neither reachable nor able to reach you, not without breaking the speed limit that light itself obeys. Physicists have plain, workmanlike names for these relationships, and they're worth sitting with, because the words themselves carry the whole idea. Two events are called time-like, separated if one lies inside the other's light cone, meaning there's enough time between them, relative to the distance involved, for something moving at or below the speed of light to travel from one to the other. Your birth and this very moment of you lying here listening are time-like separated. So is the striking of a match, and the flame that follows a fraction of a second later. There was enough time for the cause to physically reach across and produce the effect. Two events are called space-like separated, if they sit outside each other's cones entirely, too far apart in space, or too close together in time, or both, for anything. Not light, not sound, not the fastest signal physics allows, to get from one to the other before it's already too late. Imagine a firework exploding over a city at the very same instant, as far as any clock in that city could tell, that a birthday candle is blown out somewhere on the opposite side of the planet. Neither event could possibly have caused the other. No signal, however fast, could have crossed that much distance in that little time. Sirs, they are, In the language of the diagram, space-like apart, cut off from each other by the sheer geometry of space and time together. And there's a third case, right at the boundary, where light itself just barely makes the trip, arriving at the very last possible instant. So as they are, that's called a light-like or null separation, the edge of the cone itself, the knife-edge case where a beam of light leaving one event arrives at the other with no time to spare. This sorting isn't just bookkeeping, it's the whole reason causality holds together the way it does. Because here's the thing about that time-like region, the ones safely tucked inside the cones, every observer, no matter how fast they're moving or which direction, no matter what strange and stretched version of time and space their motion gives them, will agree on the order of two time-like separated events. Everyone agrees the match strikes before the flame appears. Everyone agrees your birth came before this moment. That ordering is locked in, unshakable, a genuine fact about the structure of events, rather than a matter of anyone's particular viewpoint. But space-like separation is a different animal entirely. Because those two events, the firework and the candle, are so far apart, relative to the time between them, that different observers, moving at different speeds relative to each other, can actually disagree about which one happened first, not because anyone's clock is broken, and not because anyone is being fooled. It's a genuine, physically real difference in how the passage of time carves up events for observers in relative motion, the same strange effect that stretched a traveler's years into decades back on Earth, just now showing up in a different guise. For events far enough apart, close enough together in time, which came first, simply isn't a question with one universal answer. It depends on who's asking, and how fast they happen to be moving while they ask it. Which sounds, at first, like nothing more than an odd bit of bookkeeping trivia, a curiosity for physicists to argue over. But sit with it a little longer, and something more unsettling creeps in. As long as nothing can travel faster than light, as long as every cause stays safely tucked inside its effects past light cone, the disagreement about ordering never actually matters, because no message, no influence, no signal of any kind ever needs to cross that space-like gap in the first place. The disagreement stays harmless, a mathematical curiosity about viewpoints rather than a genuine crack in the order of events. But suppose, just suppose, that something could cross that gap. Suppose a signal, or a ship, or some clever trick of physics could reach outside the cone entirely, could travel faster than light, and touch a point in that space-like region, the region where the very order of events isn't fixed, isn't agreed upon by everyone. What would that mean for cause and effect themselves? That's the question worth carrying gently into the next part of this story, the way you might carry a lit candle into a still, dark room, cupping the flame carefully, watching to see what it reveals.
Let's set that candle down for a moment, because to see what it reveals, we need to leave the language of light cones and viewpoints behind, and ask a much more concrete question. Not, can the order of events change, but has anyone ever actually written down a physically consistent description of the universe in which you could travel back to an earlier point in your own timeline? And the surprising answer, the one that keeps physicists up at night in a very particular way, is yes, several times over. Long before anyone worried about building such a thing, mathematicians and physicists found that the equations allowed it. The place to start is a phrase that sounds almost too tidy to be real physics: the closed time-like curve. Picture a path through space-time the way you might picture a road on a map, a road that a clock or a spaceship or a person could travel along
while always moving forward through their own local time, the way you always experience time, one ordinary second after another, coffee cooling, candle burning down. Now imagine that road doesn't run off toward the horizon. Imagine it curves back on itself, like a racetrack instead of a highway, so that if you keep driving forward, always forward, you eventually arrive back at a place you've already been. Not a place that looks like where you started, the very same place, the very same moment, the very same you, still mid-sip of the same cup of coffee. That looping road is what physicists mean by a closed time-like curve. It isn't a spaceship, or a wormhole, or a machine. It's a shape, a mathematical possibility baked into the geometry of a particular solution to Einstein's equations, the same equations that describe orbiting planets and bending starlight, just explored in a much stranger corner of their possibility space. And here is the detail worth turning over slowly, the way you'd turn over a smooth stone in your palm before sleep. Einstein's equations don't come with a warning label that rules these loops out. General relativity describes how matter and energy curve spacetime, and spacetime, once curved, tells matter how to move. Nowhere in that relationship is there an automatic rule insisting the curves must always run in one direction, must always avoid folding back on themselves. Whether closed time-like curves show up in a given solution depends entirely on what you assume the universe is filled with, how it's shaped, how it's spinning, if it's spinning at all. Change those ingredients, and sometimes, mathematically, the loops appear. The first person to notice this, really notice it, and take it seriously, was a mathematician named Kurt Gödel, better known for a completely different kind of loop, the strange, self-referential proofs in logic that showed certain mathematical systems could never fully prove their own consistency. Gödel and Einstein were, for a time, close friends and walking companions at the Institute for Advanced Study in Princeton, two men from very different corners of Europe, often seen strolling the quiet paths together, discussing physics, philosophy, the nature of time itself. And in 1949, as something of a gift for Einstein's 70th birthday, Gödel handed him a new solution to his own equations. Gödel had found a description of a universe filled with rotating matter, a cosmos slowly turning on itself rather than expanding the way ours does, and in that rotating universe, he showed, closed time-like curves exist everywhere. Anyone patient enough and equipped with a fast enough spaceship could, in principle, travel along one of these loops and arrive back before they left. It's worth pausing on how unsettling this was to Einstein himself. He didn't dismiss it. In his later reflections, he admitted the result disturbed him, precisely because it came from his own field equations, honestly applied, with no cheating, no exotic trickery smuggled in. The trouble wasn't that Gödel had broken the rules. The trouble was that the rules, taken seriously, seemed to permit something deeply strange. Our own universe, as far as every measurement so far can tell, isn't rotating in the way Gödel's toy universe rotates, so this particular loophole doesn't seem to apply to the actual cosmos we live in. But it planted a seed that never really stopped growing, the realization that the mathematics of gravity, left to its own devices, doesn't forbid time loops on principle. It only forbids them under certain conditions, and those conditions turn out to depend on details about the universe that have to be checked, not assumed. Once that seed was planted, other physicists went looking for closed, time-like curves in settings that felt a little less like an entire universe rotating, and a little more like something you could, at least in principle,
Imagine building. One of the more famous proposals came from a physicist named Frank Tipler in the 1970s, who worked out that an extremely long, extremely dense cylinder, spinning fast enough that its surface moved at a sizable fraction of the speed of light, would drag the spacetime around it into a kind of vortex, a whirlpool not of water, but of time and space themselves. Get close enough to such a cylinder, follow the right looping path around it, and the equations say you could, in principle, return to your own past. The kind of fine print that tends to get left out of the more breathless retellings. The cylinder has to be infinitely long, or so close to infinite, that the effect works, because a finite cylinder's gravity behaves differently at the ends, in ways that spoil the trick. An infinite cylinder is not a blueprint. It's a thought experiment wearing the clothes of an engineering proposal, useful for finding out what the equations allow, but not something any civilization, however advanced, could actually pour concrete for. A cousin of this idea involves something called a cosmic string, a hypothetical thread of impossibly concentrated energy, thinner than an atomic nucleus but potentially stretching across light years, left over, so the theory goes, from the earliest fractions of a second after the Big Bang, when the infant universe was cooling unevenly and different regions locked into different configurations, leaving defects behind the way a lake freezing quickly can leave cracks and seams in the ice.
No one has ever detected a cosmic string. They remain purely theoretical, a prediction from certain models of the very early universe, rather than an observed object. But if two such strings existed, and passed each other at sufficiently high speed, the calculations suggest their combined gravity could, again, warp spacetime into a loop, letting a hypothetical traveler thread the needle between them and emerge earlier than they departed. Once more, notice the shape of the requirement. Not a small machine sitting in a laboratory, two cosmic-scale objects, of a kind never yet observed, moving in a very particular, very fast, very precise way. And then there's a third family of solutions, arguably the most famous of all, hiding inside the mathematics of black holes themselves. When physicists first solved Einstein's equations for a rotating black hole, a solution found by Roy Kerr in 1963, they discovered something odd, buried deep in the geometry, well past the event horizon, in a region the equations describe but that no signal from inside could ever report back on. Under certain idealized conditions, the maximally extended solution contains closed time-like curves near what's called the ring singularity, and even hints at a path connecting to another universe entirely, a separate sheet of space-time glued to ours through the black hole's interior. It reads, on the page, like something out of a novel. But the honest caveat, and it's an important one to hold on to gently rather than let slip away, is that this is the mathematics of an idealized, eternal, undisturbed black hole, one that has always existed and always will, never formed by a collapsing star, never perturbed by so much as a falling grain of dust. Real black holes form. They have a beginning, and the moment you introduce that realism, most physicists suspect, though it isn't fully settled, that the exotic interior structure gets washed away, replaced by something far more violent and far less hospitable to any traveler hoping to pass through. So here,
Gathered together in this quiet room we've carried our candle into are the major roots, a rotating universe that isn't ours, an infinite cylinder that can't be built, colliding cosmic strings never yet observed, and the idealized heart of a black hole that real collapse may well destroy before anyone could reach it. 4 solutions to one set of equations, each one mathematically honest, each one physically almost impossibly out of reach. Which raises the next question naturally, the one worth letting settle like a held breath before we breathe out slowly and follow it. Let's set those 4 strange solutions aside for a while and turn to a different kind of shortcut. One that doesn't ask you to travel backward through time so much as sideways through space, in a way that happens to fold time along with it. This is the wormhole, and if the closed time-like curves we just left behind felt like distant, almost architectural curiosities, wormholes feel more intimate, more like something you could picture holding in your hands. Take a sheet of paper. Draw 2 dots on it, far apart, one near each edge. If you have to travel between them along the paper's surface, you're stuck with the whole distance, every inch of it. But you're holding a sheet of paper, not a rigid law of nature, so you can fold it. Bring the 2 dots together, and now, if there happened to be a tunnel connecting them straight through the folded gap, the distance collapses to almost nothing. That's the whole idea, at its gentlest. Space-time, in general relativity, isn't a fixed stage but a flexible fabric, and the equations don't forbid the fabric from having a handle in it, a tunnel connecting 2 regions that might otherwise be separated by billions of light years, or even, more strangely still, connecting 2 different moments in the same region. The mathematics of this was noticed early, tucked inside the very same 1935 paper where Einstein and a young physicist named Nathan Rosen were actually trying to do something else entirely. They were attempting to describe an elementary particle, like an electron, as a smooth kink in space-time geometry rather than a point, and in the process of gluing 2 black hole solutions together at their horizons, they produced a bridge. It's remembered now as the Einstein-Rosen bridge, and it's the mathematical ancestor of every wormhole discussion since. But that original bridge had a serious problem, one that took decades to fully appreciate. It pinches shut. If you trace the geometry forward in time, the throat of the bridge narrows and closes to 0 width faster than any signal, let alone any traveler, could cross it. Picture a canyon whose walls are rushing together to meet in the middle, and you're trying to walk from one side to the other while the gap seals ahead of you and behind you at the same time. No speed helps. The bridge simply isn't open long enough to use. This is where the word traversable starts to matter, and it's a word physicists chose carefully. A wormhole can exist mathematically as a valid solution to the equations and still be completely untraversable, meaning the throat closes too quickly for anything, even a beam of light, to get through before the geometry seals. For decades, this was assumed to be true of every wormhole solution, an interesting curiosity, but not a shortcut, more like a locked door glimpsed through a keyhole. Then, in 1988, 2 physicists working at Caltech, Michael Morris and Kip Thorne, asked a very specific and very practical question. Thorne, the story goes, had been approached by his friend Carl Sagan, who was writing a novel and wanted his character to travel to a distant star without breaking the speed of light, and wanted the physics to at least be defensible. So Morris and Thorne turned the usual method of general relativity backward. Normally, you start with a distribution of matter and energy and solve for the geometry it produces. Instead, they started by writing down the geometry they wanted, a wormhole with a throat that stayed open, smooth and gentle enough for a human being to fall through without being harmed, and then asked what kind of matter and energy would be required to hold that shape in place. The answer they found is the crux of the whole subject, and it's worth sitting with slowly. To keep a wormhole throat propped open against its own gravity's tendency to pinch it shut, you need something that pushes outward at the throat rather than pulling inward, and in the language of general relativity, that means negative energy density, or more precisely, a violation of what are called the energy conditions, the mathematical assumptions that ordinary matter obeys. Ordinary matter, the stuff of stars and stones and bodies, always has positive energy density, as measured by any observer, and always attracts gravitationally. What holds a traversable wormhole throat open is often called exotic matter, not because it's unusual in the sense of being rare, but because as far as we know from everyday physics, nothing behaves this way in bulk. It's matter that would seem, in a very loose sense, to gravitationally repel rather than attract, at least in the region right at the throat. Here's where it gets genuinely interesting, rather than simply exotic for exotic's sake, because negative energy density isn't purely science fiction. It shows up in a real, measured, laboratory phenomenon called the Casimir effect, named for the Dutch physicist Hendrik Casimir, who predicted it in 1948. If you place two uncharged, perfectly parallel metal plates extremely close together in a vacuum, closer than the wavelength of many of the virtual particle fluctuations that quantum theory says are always fizzing in and out of empty space, something curious happens. The plates restrict which wavelengths of these fluctuations can exist between them, while outside the plates, every wavelength is still allowed. This imbalance produces a tiny but measurable force pulling the plates together, and it has been confirmed experimentally many times since the 1990s, with increasing precision. The energy density between the plates, in a real and doable calculation, comes out negative relative to ordinary vacuum. So negative energy density is not forbidden. It exists in tiny, fleeting, laboratory-scale amounts. The trouble is one of scale, and this is the sobering part physicists return to, again and again. The Casimir effect produces negative energy density in a gap a fraction of a hair's width across, using plates you could hold in your palm, and the effect is minuscule, requiring extraordinarily sensitive instruments to detect it all. Holding open a wormhole throat large enough for a person, or even for a single photon carrying information, seems to require negative energy on a scale so enormous, so sustained, and so precisely shaped that nothing in known physics offers a mechanism to produce it.
This is where a family of results, called quantum inequalities, becomes important, developed largely by the physicist Lawrence Ford and his collaborators starting in the 1990s. These inequalities are a kind of accounting law for negative energy in quantum field theory. They don't say negative energy is impossible. They say that if you borrow it, the way you might borrow against a budget, the amount you can borrow and the length of time you can hold it are related by a strict trade-off. A little negative energy for a little while is allowed. A lot of negative energy, sustained for any meaningful length of time, runs up against limits that seem to make holding open a traversable wormhole, at human scales, extraordinarily difficult, and by some estimates, essentially impossible with any energy source we can imagine building.
Even setting that enormous hurdle aside for a moment, there's a second worry, a question of stability rather than construction. Suppose, somehow, a wormhole throat existed and was briefly open. What happens the instant something passes through it? Several physicists in the 1990s, including Sung-Won Kim and Kip Thorne himself, studied this and found reason for concern. Any realistic wormhole connecting two different times would tend to act like a lens for its own radiation, drawing in stray light and particles from the wider universe and looping them through the throat again and again, each pass adding a little more energy in a kind of runaway feedback that could pile up and destroy the throat before a traveler ever arrived. It's a bit like trying to keep a door propped open in a hurricane, where the very wind rushing through threatens to slam it shut, except here, the wind is generated by the doorway's own geometry. But let's follow the thought experiment through anyway, gently, because it's this next part that connects wormholes back to everything we've discussed about time. Picture a wormhole not as a tunnel between two places, but as a tunnel with two mouths sitting in the same room, like the two ends of a single length of hose, curled around so both openings face you. If you take one mouth, seal it inside a spacecraft, and send that spacecraft on a long journey at a good fraction of the speed of light, then bring it home, something remarkable falls directly out of special relativity, the very same time dilation we spent an earlier section on. The traveling mouth experiences less elapsed time than the stationary one, exactly the way a traveling twin ages less than a twin who stayed home. But the wormhole still connects the two mouths directly through its throat, a shortcut through the folded geometry rather than through the long way around. So stepping into the mouth that stayed still and stepping out the mouth that traveled could mean stepping out into an earlier moment than the one you left, not because you outran light through ordinary space, but because the two doorways now disagree about what time it is, the way two clocks that travel different paths always do.
Let your shoulders settle a little further into the mattress now, because we're about to sit with the question that probably occurred to you the moment anyone first mentioned time travel to you, maybe when you were young enough to ask it out loud without embarrassment. What happens if you go back and stop your own grandparents from meeting? It's called the grandfather paradox, though the earliest version of it in print, from a French science fiction writer named René Barjavel in 1943, actually involved a man stepping on his own ancestor by accident, not murdering anyone on purpose. Barjavel called his book Le Voyageur Imprudent, the careless traveler, and the name fits, because the whole problem hinges on carelessness, on the idea that a person moving backward through time could disturb something small and distant that turns out to matter enormously. If you prevent your grandfather from meeting your grandmother, then you are never born. If you are never born, you cannot travel back in time. If you cannot travel back in time, your grandfather is never stopped, and so he does meet her after all, and so you are born, and so you do travel back, and the loop closes on itself and immediately springs back open, forever, like a seesaw with nobody sitting on either end to settle it. Physicists don't usually treat this as a proof that time travel is impossible. They treat it as a proof that certain kinds of stories about time travel are impossible, which is a gentler and more interesting distinction. Think of it less like a wall and more like a sentence that cancels itself out, the way saying, "This sentence is false," doesn't break language in general,
It just means that particular sentence can't be evaluated the ordinary way. The grandfather paradox works the same way. It rules out timelines that are self-erasing, timelines that contain their own contradiction, but it doesn't automatically rule out every timeline that includes a loop. This is where a Russian physicist named Igor Novikov enters the story, in the 1980s, working partly with Kip Thorne's group as they were puzzling over wormholes and closed time-like curves, the technical name for any path through spacetime that loops back to touch its own past. Novikov proposed something now called the self-consistency principle, and it's worth turning over slowly because it's a genuinely strange piece of reasoning, the kind of idea that sounds almost too tidy until you notice how carefully it avoids saying anything mystical. Novikov's idea was this: if the laws of physics permit a closed loop in time, then the only things that can actually happen inside that loop are things that are self-consistent, things that don't contradict themselves. Not because some cosmic censor is watching and correcting mistakes, but for the same reason a jigsaw puzzle piece only fits one way. You can try to force it, but if the shape is wrong, it simply won't go in. No rule against it, no punishment for trying, just a plain geometric fact about which arrangements are possible and which aren't. Under this view, if you traveled back in time, intending to prevent your grandparents from meeting, something would always, without exception, interfere with your plan. Your car would break down, you'd trip on the stairs, you'd fall in love with your own plan, and lose your nerve. Not because the universe is protecting itself, exactly, but because the version of events where you succeed was never actually a possible solution to begin with, any more than a circle can secretly have corners. There's a lovely, almost funny thought experiment physicists use to illustrate this, sometimes called the billiard ball problem, worked out in detail by a group including Novikov, Thorne, and others in the later 1980s. Imagine a billiard ball rolling toward a wormhole mouth sitting on a pool table. It enters the mouth, travels back in time a few seconds, and emerges from the other mouth earlier than it went in, on a path that would knock its earlier self off course before it ever reaches the wormhole at all. You'd think this guarantees a contradiction, the ball stopping itself from ever making the trip that created the time-traveling ball in the first place. But when the physicists actually worked through the mathematics of the collisions, trajectory by trajectory, they kept finding self-consistent solutions instead, ones where the future ball gives the past ball a gentler nudge, deflecting it just enough that it still enters the wormhole, just along a slightly different path than it would have taken otherwise. The loop closes smoothly. Nothing is erased. It's a bit like watching two dancers who've never rehearsed together somehow avoid colliding on a crowded floor, not through any conscious effort, but because the only paths that actually exist are the ones that don't collide. If you find that satisfying, hold on to it gently, because there's a very different way of resolving the same paradox, and it doesn't ask reality to be quite so accommodating. This is the branching history idea, sometimes discussed in connection with the many worlds interpretation of quantum mechanics, though it's worth being honest that this connection is speculative and not something quantum mechanics itself requires. Under this view, when you travel back and prevent your grandparents from meeting, you don't erase yourself from existence, and you don't get mysteriously thwarted by falling pianos and lost car keys. Instead, your action simply peels off a new branch of history, a parallel timeline where your grandparents never meet, existing alongside, not instead of, the original timeline where you were born and grew up,
and eventually stepped into a machine. You didn't undo your own birth. You just started a second story, running in parallel, the way an author might write two different endings to a novel without either one canceling the other out, both existing, bound in different books or different chapters, neither one lying about what happened in the other. This is a comforting picture in some ways, because it removes the eerie sense that the universe is subtly steering your actions to prevent contradictions, wearing away at your free will like water shaping a stone. Under branching histories, you can do anything you like. There's no invisible hand nudging billiard balls or breaking down cars. But it comes at its own cost, because it means the traveler who set out to fix a mistake, to save someone, to prevent some grief, never actually returns to the world they left. They step out into a neighboring branch instead, one where their original timeline, with the original unsaved person, carries on completely unaffected somewhere else, unreachable, still grieving. It solves the logical paradox, but leaves an emotional one in its place, and it's worth sitting with that for a moment, because a lot of the appeal of time travel stories is the fantasy of going back and changing something you regret, and branching histories quietly take that fantasy away, even while removing the contradiction that made it impossible in the first place. Neither of these ideas, Novikov's self-consistency or branching histories, has been tested, and neither can easily be tested, since as far as we currently understand physics, no closed time-like curve has ever been observed, and building one may not even be possible, given the negative energy problems we walked through with wormholes. They're best understood as two different ways of asking what would have to be true if closed loops in time existed at all, two answers to the same hypothetical question, favored by different physicists for different reasons, neither one crowned as the winner. Some physicists lean toward self-consistency because general relativity's equations, when you actually try to solve them for a space-time containing a time loop, tend to produce single, consistent, complete solutions rather than paradoxical dead ends, which is itself a kind of evidence, though a mathematical rather than an experimental one. Others find the many branches picture more physically natural, an extension of ideas already present in quantum theory, rather than a new rule invented specifically to patch up time travel. There's a third idea worth mentioning before we drift onward, quieter than the other two, and it goes by the name of the bootstrap paradox, sometimes called an information paradox, though it's a different kind of information paradox than the one associated with black holes. Picture an object, or an idea, or even a piece of music that seems to come from nowhere at all, its origin looping endlessly through time without ever actually being created anywhere.
Let's set the bootstrap paradox aside for now, half finished, the way you might set down a book at the end of a chapter, and turn toward a completely different branch of physics, one that seems, at first, to have nothing to do with time travel at all, and yet keeps getting dragged into these conversations, whether it wants to be there or not. That branch is quantum mechanics, and the reason it keeps showing up is a phenomenon called entanglement, which Einstein himself found so unsettling that he called it spooky action at a distance, a phrase that has outlived almost everything else he ever said informally. Here is the calm version of what entanglement actually is. Imagine two coins that have been prepared together in a very particular way, then carried apart, one to Frankfurt and one to some quiet town on the other side of the world. Under ordinary circumstances, flipping one coin tells you nothing about the other, but an entangled pair
behaves differently. If you flip one and it lands on heads, the other, the instant it's checked, will land on tails, every single time, no matter how far apart they've traveled or how little time has passed since the first flip. This isn't a metaphor for some hidden mechanical link, some string running between them. As far as decades of careful experiments can tell us, the two particles don't have a definite state at all until one of them is measured, and then, somehow, both halves of the pair snap into a matching arrangement together, immediately. It's natural, hearing that, to think you've just found a loophole for sending messages faster than light, maybe even backward through time. If measuring one particle instantly affects its distant partner, why not encode a message in the pattern of measurements and read it off on the other end before a light signal could have arrived? Physicists ask this question seriously, right from the beginning, and the answer, worked out carefully over the 20th century, is that you can't, and the reason why is oddly comforting once you sit with it. The problem is that the outcome of any single measurement on an entangled particle is random. You flip your coin in Frankfurt, and it lands on heads, but you had no way to choose that outcome in advance. It could just as easily have landed on tails. Your partner across the world, checking their coin, will indeed find the opposite result, tails, and there is a real correlation there, verified in experiment after experiment since the 1970s and 80s, most famously in tests inspired by the physicist John Bell, who in 1964 worked out a precise mathematical way to check whether quantum correlations could be explained by any hidden, ordinary, everyday kind of shared information. They couldn't be, it turned out, and that's remarkable. But remarkable is not the same as useful for sending a signal, because your partner has no way to know, just by looking at their own coin, whether their tails outcome was caused by your measurement, or would have happened anyway, or happened before you even flipped your coin, or after. From their side, alone, with just their own results in hand, it looks exactly like random noise. The message, if there is one, is invisible until you compare notes, and comparing notes means sending information the ordinary way, by phone call, by radio signal, by any method that respects the speed of light. Only once both sets of results are brought together, the honest way, does the correlation become visible. So entanglement is real, and strange, and confirmed beyond reasonable doubt, but it carries no usable message on its own. It's less like a telephone, and more like two people opening identical, sealed envelopes on opposite sides of the planet, and discovering, to their mutual astonishment, that the notes inside always contradict each other in a precise pattern neither one controlled. This limitation has a name, worked out formally in the 1980s, called the no communication theorem, and it holds up under all the strange elaborations physicists have layered onto entanglement since, including one particularly dizzying idea called quantum teleportation. Teleportation, in this context, doesn't mean beaming a person or an object physically from one place to another, the way it does in science fiction. It means something narrower and, in its own way, more interesting. Using an entangled pair, a shared resource prepared in advance, it's possible to transmit the exact quantum state of one particle onto a distant particle so that the second particle ends up in precisely the condition the first one was in, as though the information itself had crossed the gap. This was demonstrated experimentally for the first time in 1997 by a team led by the physicist Anton Zeilinger in Innsbruck, and it has since been done over longer and longer distances, including between ground stations and orbiting satellites. But here's the quiet detail that keeps this from being time travel
or faster than light communication, and it's easy to miss if you're only half paying attention, which is, of course, exactly the mood we're in right now. Quantum teleportation still requires that ordinary, mundane, light-speed limited channel we mentioned a moment ago. After the measurement is made on the sending end, the result, two simple classical bits of information, has to be physically carried to the receiving end, by cable, by radio wave, by whatever means, before the receiving particle can be adjusted into the correct final state. Without that classical information arriving the slow way, the particle on the receiving end just sits there in a kind of useless, unresolved condition, statistically identical to noise. The entanglement does something remarkable, but it doesn't skip the trip. It's a bit like being handed a locked box on one continent, along with the promise that its twin has just been handed to someone across the ocean, except you still need to receive a phone call telling you the combination before the box means anything at all. There's a related family of experiments, called delayed choice experiments, that tend to get described in especially breathless language, and they deserve a gentler retelling. The idea traces back to a thought experiment proposed by the physicist John Wheeler in 1978, and it goes roughly like this. In certain versions of the classic double-slit experiment, where light behaves like a wave when unobserved, and like a stream of particles when measured, you can arrange things so that the choice of whether to measure which path a photon took is made after the photon has already passed through the slits, seemingly after it should have already decided how to behave. Actual laboratory versions of this were carried out starting in the 2000s, using clever optical setups, and the results are consistently strange, matching quantum theory's predictions, rather than any intuitive picture of a particle traveling along one definite path the whole time. It certainly feels, reading about it late at night, like the photon's past behavior is being reached backward and altered by a decision made in its future. But careful analysis, the kind done by physicists rather than headline writers, shows that nothing is actually being sent backward in time here either. What's happening is subtler, and honestly, more interesting than time travel would be. The photon never had a definite, hidden path to begin with, not before the measurement, and not after, so there's no fact being changed after the fact, because there was no settled fact in the first place. Quantum theory doesn't describe particles traveling secretly along one path, while we simply fail to notice. It describes something closer to a spread of genuine possibilities that only resolves into a definite outcome at the moment of measurement, and delayed choice experiments confirm that this resolution genuinely can't be pinned to any earlier moment, without requiring any signal or influence to physically travel backward through the intervening time. It rewrites our intuitions about when and how facts become facts, rather than rewriting facts that were already settled. There's one more idea drifting through the more speculative corners of this field, quieter still, called indefinite causal order, and it comes from thinking hard about post-selection, the practice of running an experiment many times over, and only paying attention to the results that meet some particular condition afterward, discarding the rest. In ordinary physics, event A happens, then causes event B, in a fixed sequence, cause before effect, always. But in certain carefully constructed quantum experiments, first explored theoretically in the early 2010s, it's possible to build situations where asking whether A caused B, or B caused A, simply doesn't have a single correct answer. where the causal order itself exists in something like a superposition, undetermined until you look closely at how the experiment was arranged. It doesn't let anyone send a message to yesterday, and no one building these setups believes it will, but it does gently loosen one more brick from the wall we usually assume separates past from future, cause from effect, and it's a good, strange place to rest for a moment before we turn to a very different, much older way people have tried to make sense of time's stubborn one-way flow.
Let's rest there, in that strange loosened brick, and drift backward for a while, all the way to before physics had the vocabulary for any of this, back to campfires and oral traditions, because people were telling stories about broken time long before anyone had the mathematics to describe it. Ancient folklore is full of travelers who slip outside ordinary time without ever touching a machine. There's the Japanese fisherman Urashima Taro, who visits an undersea palace for what feels like a few days and returns home to find centuries have passed, everyone he loved long dead. There are Celtic tales of mortals wandering into fairy mounds for a single evening of music and dancing, only to stumble back out into a world decades older. Washington Irving's Rip Van Winkle falls asleep for 20 years under the weight of an enchanted drink and wakes to a country that has fought a revolution without him. Notice what these stories share. They're almost always about time moving strangely for one person while flowing normally for everyone else, not about anyone choosing to travel to a specific year and interfering with events. There's no going back to fix anything, no meeting your grandfather, no changing history. That idea, deliberate, navigable travel through time as a kind of controllable journey, had to wait for a very particular moment in the 19th century, when trains and telegraphs were making people newly comfortable with the notion that different places could be connected instantly, and that distance itself was something you might engineer your way around. That moment arrived, more or less, in 1895, with a young English writer named Herbert George Wells, working as a science journalist and struggling novelist, who published a short book called The Time Machine. Wells did something nobody had quite done before. He didn't send his time traveler into a dream, or a magical sleep, or a fairy realm. He gave him a machine, with a saddle, and instruments, and quartz rods, deliberately engineered to move through time the way a bicycle moves through space, and it's worth sitting with how genuinely strange that idea was for its era. Wells has his unnamed inventor explain, in a small dinner party framed as a lecture, that time is simply a fourth dimension, that just as a cube has length and width and height, every object also has duration, and that if you can move freely through the first three dimensions, there's no logical reason you couldn't build a device to move through the fourth as well. This was, remarkably, 10 years before Einstein published anything about relativity. Wells wasn't doing physics. He was doing something more like philosophical guesswork, dressed up as fiction, but the guess turned out to brush up against something real, because when Einstein and his teacher Hermann Minkowski later gave the fourth dimension a rigorous mathematical treatment, the deep structural kinship between time and space that Wells had imagined for storytelling purposes turned out to have genuine physical teeth. Einstein's own path there began not with time travel at all, but with a much narrower, more technical puzzle about light and electricity, worked out largely alone in 1905 while he held a day job examining patent applications in Bern, Switzerland. Special relativity, as he called the resulting theory, showed that time doesn't tick at the same rate for everyone. It stretches and compresses depending on how fast you're moving
relative to something else, a genuinely measurable effect, and not an illusion of perception. 10 years later, working through an even harder problem, Einstein extended this into general relativity, describing gravity not as an invisible force reaching across space, but as the bending of space and time themselves, by mass and energy. The way a heavy object, placed on a stretched rubber sheet, makes nearby marbles roll toward it, not because it's pulling them, but because it's reshaped the surface they're rolling on.
This is where things start to become genuinely relevant to time travel, because if massive objects can bend the shape of space-time, and if space-time's shape determines the paths that clocks and calendars are free to follow, then it becomes at least conceivable, mathematically, that space-time could be bent so severely it curves back on itself. It was Hermann Minkowski, actually, not Einstein, who gave us the most useful picture for thinking about all this, in a lecture delivered in Cologne in 1908, where he famously told his audience that space and time, taken separately, were doomed to fade into mere shadows, and only a union of the two would preserve an independent reality. Minkowski space-time treats every event, everywhere and every when, as a single point in a four-dimensional block, and every object's entire history, from birth to death, becomes a kind of stretched-out line drawn through that block, called a world line. It's a strange but useful way to picture your own life, not as a single dot moving through a series of present moments, but as an entire thread-like shape already laid out, past and future both, the way a long-exposure photograph captures the full arc of a sparkler being waved through the dark. Ordinary world lines only bend forward, tracing out one moment after another in the usual order. But once you have the mathematics of curved space-time available, a natural, almost irresistible question opens up. Are there solutions to Einstein's equations where a world line could loop back around and rejoin its own past, forming what physicists call a closed time-like curve? It was here that a quiet, intensely private mathematician entered the story, one of the more startling episodes in the whole history of this subject. Kurt Gödel, already famous for his incompleteness theorems, which had shaken the foundations of mathematical logic itself, spent the 1940s at the Institute for Advanced Study in Princeton, where he became close friends with Einstein, the two of them often walking home together deep in conversation. As something of a birthday gift for Einstein's 70th birthday in 1949, Gödel worked out an exact solution to the equations of general relativity, describing an entire rotating universe, and discovered, to what one imagines was his own considerable fascination, that in such a universe, closed time-like curves are mathematically permitted. A hypothetical traveler with a sufficiently powerful spaceship could, in principle, trace a path through this rotating cosmos and arrive back at their own past. Gödel wasn't proposing this as a serious travel itinerary. He seems to have been more interested in what it implied philosophically, that if general relativity allowed such solutions at all, then the theory itself seemed to permit the past to be, in some sense, still reachable, which unsettled his intuitions about the nature of time passing the way it unsettles most people's. Our own universe, as far as anyone can tell, isn't rotating in the way Gödel's toy model required, so this solution was never meant as a blueprint. But it opened a door that has never fully closed since. General relativity, taken purely as mathematics, does not by itself forbid time travel into the past. Other exact solutions were found in later decades, involving infinitely long spinning cylinders, or wormholes held open by exotic negative energy, or cosmic strings passing near one another at enormous speed, each one another mathematically legal, but physically extravagant loophole. This pattern,
A theory permitting something on paper that seems to strain plausibility is exactly what led the physicist Kip Thorne and his students to formalize wormhole time machines in the late 1980s, and exactly what prompted Stephen Hawking, a few years later, in 1992, to propose his chronology protection conjecture, the idea we touched on earlier, that some deeper law of physics likely steps in to prevent these loopholes from ever actually being realized, even if nobody has proven such a law from first principles. Hawking's own suspicion, offered with his characteristic dry humor, was that the universe seems to conspire to keep history looking consistent, that quantum effects would flood any nascent closed time-like curve with runaway energy and destroy it before it could ever be used. It remains a conjecture rather than a theorem. It might be right. It might eventually be shown wrong, or shown to need refining once physicists have a working theory of quantum gravity. And that, in the end, is the honest note this history has to land on, because the science here is genuinely unfinished.
General relativity, magnificent as it is a classical theory, one that doesn't yet know how to speak the language of quantum mechanics. And every serious physicist studying this subject expects that whatever final answer exists about the fate of closed time-like curves will require a full theory of quantum gravity to sort out properly, something string theorists and loop quantum gravity researchers have been chasing for decades without full success. What could actually move this from speculation toward settled science isn't more elegant equations sitting on a chalkboard, but new kinds of evidence. Precision tests of relativity near extreme gravitational environments, like the region around a spinning black hole, gravitational wave detectors picking up signatures from cosmic strings if any exist, laboratory experiments probing whether negative energy densities can be sustained at scales relevant to exotic spacetime geometries, or theoretical breakthroughs that finally show, one way or another, whether quantum gravity enforces something like Hawking's conjecture as a genuine law rather than a hopeful guess. None of that exists yet. What exists is a century and a half of steadily sharpening the question, from firesides and fairy mounds to a young journalist's bicycle through time, to a homesick mathematician's birthday gift to his best friend, each step making the puzzle less like a story and more like an open problem with real mathematics attached to it, waiting quietly for whichever generation of physicists finally gets to test it properly. Let it settle, then, all of it. The whole long arc we've walked together tonight. Think back to where we began, with nothing more exotic than a clock ticking on a mantle. The plain and unremarkable fact that you move through time whether you want to or not, 1 second at a time, always forward, the way a leaf on a stream moves downstream without ever choosing to. That was the first quiet mystery, even before we brought in rockets or black holes. Time passes. You did not agree to this. It simply happens, and it has been happening to every creature that ever lived, from the first stirring of something like awareness in some ancient sea, all the way to you, right now, warm under whatever blanket you're under, listening to these words drift by. Then we let the story complicate itself, gently, the way a path through a forest complicates itself the deeper you walk. We found that forward motion isn't as uniform as it feels from the inside. A clock on an airplane and a clock resting quietly on a shelf do not agree with each other, not by much, but by a real and measurable amount, and the disagreement isn't a flaw in the instruments. It's a fact about the shape of time itself, which turns out not to be the fixed, universal backdrop that Newton imagined, but something more like a fabric, something that can stretch, depending on how fast you're moving relative to somebody else. Two people can leave the same room and return to it having lived through different amounts of time, both of them correct, both of their clocks telling the truth. That was the twin who stayed, and the twin who traveled, one of them aging faster, simply because the other went somewhere and came back. And then, gravity joined the story, because it turns out that speed isn't the only thing that bends time. Mass does it too. A clock at the base of a mountain runs very slightly slower than a clock at the summit, not because the clocks are different, but because time itself moves more sluggishly deep in a gravitational well, the way a heavy stone sinks slower through honey than through water. Stand near something as massive as a black hole, and the effect stops being subtle. It becomes dramatic, almost theatrical, time stretching and thickening, the closer you get to that dark boundary where light itself can no longer climb back out. We didn't need spaceships or exotic machinery for any of this. We only needed the universe to be exactly as strange as it already is. From there, we went looking at light, because light turned out to be the one thing that refuses to bend the rules no matter how you chase it. However fast you run, light keeps outrunning you at the same steady speed, and that stubbornness is what forces space and time to bend instead. We drew those quiet diagrams of light cones, the shape of everything you could possibly reach spreading outward from you like ripples on a pond, and the shape of everything that could possibly have reached you spreading backward the same way. Between those two cones sits everything causally connected to this exact moment of your life. Outside them sits everything that simply isn't part of your story yet, or ever, unless something changes. It's a strange kind of comfort, honestly, to think of your life this way, as a single point moving steadily upward through a cone of light, always safely wrapped inside the boundary of what can affect you and what you can affect in turn. We asked, gently and without rushing, whether it might be possible to step outside that cone altogether, to reach backward instead of only forward. And that's where the real strangeness began, tunnels through space-time that mathematics allows even though nature has never shown us one. Bridges connecting one region of the universe to another, the way a shortcut connects two ends of a long hallway. We spoke of the kind of exotic matter such a bridge would need to stay open, matter with properties nothing we've ever observed actually possesses, and we spoke of spinning cylinders and cosmic strings, mathematical curiosities that let time bend back on itself under conditions so extreme they may never exist anywhere in this universe, or any universe. And then, unavoidably, we sat with the paradoxes, because if you could somehow travel backward, logic starts to wobble in interesting ways. What happens if you prevented your own beginning? What happens if information arrives from nowhere, a melody remembered before it was ever composed, a proof discovered before anyone thought of it first, looping endlessly, with no true origin at all? We didn't rush past these. We let them sit, turning them over slowly, the way you might turn a strange stone over in your palm by firelight, noticing its odd angles without needing to solve it immediately. Physicists have offered different responses to these puzzles: self-consistency that quietly forbids contradictions, branching histories that let every possibility unfold somewhere, or a deep suspicion that nature simply won't permit the machinery in the first place.
And that suspicion is where we ended, with a conjecture rather than a proof, a guess, dressed in careful mathematics, one that says the universe may protect itself from these paradoxes automatically, snuffing out any closed loop before it could ever become real. It might be right, it might not be,
That uncertainty isn't a failure of the story. It's the most honest place a story about the edge of physics can end, because this is genuinely where human knowledge runs out for now, at the border between a theory that explains gravity beautifully and a theory that explains particles beautifully, two languages that haven't yet learned to speak to each other fluently. So let all of that settle now. The fairy mounds and the bicycles built for time, the young clerk in Bern turning equations over in his mind while the rest of the city slept, the friends exchanging strange and generous gifts of pure mathematics, the decades of careful, patient work by people who mostly never got applause for it, just the quiet satisfaction of understanding something a little better than the person before them had. All of that has led here, to this moment, to you. Because underneath every equation and every diagram, there was always this simpler fact waiting patiently at the center of it all. You are traveling through time right now. You have been the entire time you were listening. Every breath you've taken since this began has carried you further along that upward path through your own personal light cone, second by second, the most ordinary kind of time travel there is, and also, if you stop to really consider it, the only kind that has ever been fully confirmed.
No wormhole required, no exotic matter, no spinning cylinder, no rocket approaching the speed of light, just the steady, unglamorous, entirely real drift of one moment into the next. And it will keep happening, whether you're awake to notice it or not. Whether you drift off in the next minute or stay listening a while longer, time will keep doing what it has always done, carrying you forward the way a river carries a leaf, without asking, without needing your permission, without needing you to understand it at all. You don't have to solve the paradoxes to be allowed to rest. You don't have to know whether wormholes are possible, or whether Hawking's conjecture will someday be proven or overturned. Those questions will still be there tomorrow, patient as ever, waiting for physicists smarter and more awake than either of us right now. For tonight, let your part in this whole vast, strange story be the simplest part, the part that every living thing has always managed without any equations at all. Let your breathing slow. Let your thoughts loosen their grip, the way a hand loosens around something it's finally ready to set down. Somewhere far above you, starlight is arriving that left its source before you were born, carrying its own small piece of the past into this present moment. And somewhere in your own body, at this very second, time is passing exactly the way it should, in the only direction that has ever felt truly familiar. You don't need a bridge through space-time tonight, only a bed and a slow breath, and permission to let the ordinary miracle of time carry you gently onward into sleep. Rest well.